All right, welcome. We are taking a look at chapter 3.9, the derivatives of exponentials and logarithms. All right, so we've done the derivative of pretty much everything else at this point. We've done the power rule for, the polynomials, for the square roots, for the radicals. We've got sine, we've got cosine. But then we have, the product rule, the quotient rule, the chain rule. We have all of these things, and we can do them. All right, so the last thing that we really have to figure out the derivative of is just these exponentials, okay? And so we're going to start with e to the x. All right, so let's use the limit definition of a derivative. So to do the derivative of e to the x at 2, step 1, we need to find f of 2, so e to the second power. All right, e to the second power is 7.389. All right, so to do the derivative of e to the x at 2, f prime of 2, we can do the limit as x approaches 2 of e to the x minus e to the second over x minus 2. Now, we can't do this, I guess, traditional method, so we're going to go ahead and try it with a table. So let's pick a number really, really close to 2, but a little bit smaller, maybe 1.999. And then a number really close to 2, but a little bit bigger, 2.001. All right, and let's see what we got. So to do this, we need to do alpha y equals make a fraction. So to get this first one, the left side limit, we're going to do e to the 1.999 minus e to the second over 1.999 minus 2. All right, and look at that, we get 7.385. If we repeat this, but instead of 1.999, 2.001, $7.392. Well, hey, do you know what's right in between 7.385 and 7.392? Yep, you guessed it, 7.389. Okay, so the derivative of e to the x at 2 is e to the second. All right, let's try this again with x equals 9. E to the 9th. Let's just see if we can figure this out again. E to the 9th is a very large number, 8,103. All right. So pick a number just a little bit smaller than 9, 8.999. Pick a number a little bit bigger, 9.001. And let's try this. So the limit definition of a derivative says e to something just a little bit smaller than 9 minus e to the 9th over a little bit smaller than 9 minus 9 or if we repeat this with number just a little bit bigger than 9, so what's right in between 8,099 and 8107? Yeah, you guessed it, 8103. So just a quick, look at this. The derivative of e at 2 is e to the second. The derivative of e at 9 is e to the 9th. What do you imagine the derivative of e to the x is for any x? Well, it is in fact itself. E is its own derivative. So the derivative of e to the x is e to the x. All right, and that is a very, very, very special aspect of this function e to the x. The general idea is that that exponential growth function is literally growing at the rate of itself. And that is one of the very, very special, interesting things about this thing. The derivative of e to the x is e to the x. All right? So that's the basic idea of this thing. It's going to become so valuable for us as we move forward in mathematics, in calculus, and calculus 2, calculus 3, differential equations, if you get there. This fact is so valuable. Okay. All right. But if we just need to use it then to do something like the derivative of e to the x squared. All right. So the square, I guess parentheses should be around that exponent. If we want to do this, well, the derivative of something with e, the derivative of e to the x is e to the x. All right. So that's the fun part. But the problem is this one has more than just an x in the e to the x part. It's more than just an x as the exponent. So we have to do the chain rule times the derivative of that extra stuff. So the derivative of x squared is 2x. All right. Usually we would put the 2x first, then the e to the x second. But there we go. We've got our derivative. All right. The derivative of e to the x over x. Well, that's a quotient. Okay, so we're going to have to do the quotient rule. The derivative of the first times the bottom left alone minus the derivative of the bottom times the first left alone over the bottom squared. All right, so we can do that. Now, natural logs are a little bit harder. Okay, now to do the derivative of a natural log, step one, we have to remember what a natural log is. Natural log is a log base e. So if we wanted to, we could rearrange a natural log to become e to the power of y equals x. I hope you remember how to rearrange logarithms. Okay, so e to the y equals x. This thing we can take the derivative of. Okay. So taking the derivative of both sides, the derivative of e to the y, well, the derivative of e to the x is e to the x, so the derivative of e to the y is e to the y. But since that's not an x, we have to do that implicit differentiation idea. So times dy dx, the chain rule, equals, it's like 1. All right, from there, we need to solve for dy dx. Okay, great. All I have to do is move this e to the y to the other side. 1 over e to the y. Cool, and then hopefully we can substitute back. Remember right here we said e to the y is the same as x. So e to the y becomes x, and we have our answer. The derivative of natural log is 1 over x. All right, so the derivative of the natural log, 1 over x. That is the next big picture idea. The derivative of e to the x is e to the x. The derivative of natural log is 1 over x. All right, so to take the derivative of this problem, I have the natural log of this polynomial. So to do g prime, well, I have something inside of a natural log, so I have to do the chain rule. The derivative of the natural log is 1 over x, but in this case, it'll be 1 over x squared plus 3x minus 4 times, the chain rule says multiply by the derivative of the inside, so times 2x plus 3. So we can just move this to the top of that fraction. Now this thing could maybe factor. If we wanted to, we could say maybe this is x plus 4x minus 1, but it won't cancel with something on the top, so we probably don't need to actually do that. All right, so let's try this one. If I'm going to take the derivative of this, well, h prime, 1 over the stuff that's inside. So x squared over 4x minus 1 times. The chain rule says the derivative of the inside. Well, unfortunately, the derivative of that inside is a quotient. So I have to do the quotient rule. All right. The derivative of the top times the bottom left alone minus the derivative of the bottom times the top left alone over the bottom squared. All right, this is a mess. So what we could do is same change flip for this first one. So keep the one the same, change to times, flip this. And this thing, we've got what? We can distribute that. 2x times 4x, that's 8x squared minus 2x minus 4x squared. All right, this 4x minus 1 can reduce with one of those 4x minus 1s. The top here, we got what? 8x squared minus 4x squared. That's 4x squared minus 2x. Cool. And it looks like maybe we could factor out 2x from that. On the bottom, we got an x squared and a 4x minus 1. It's like one of these x's could reduce. So we have this wonderful answer here. Again, we're to the derivative of a natural log with a quotient inside. So we definitely have a very strange answer. All right, one of the things, so we can do that. I hope we're okay with the chain rule. I hope we're okay with this idea the derivative of a natural log is 1 over x. All right, the thing that we're going to struggle with in this chapter, or in this section, is just some properties, okay? There are some properties of natural logs and logarithms in general, exponentials in general, that sometimes we just forget. So oftentimes these properties can really simplify the problem for us. Instead of having to do all this algebra, all this same change flip stuff, this factoring, this reducing, sometimes these properties could have been really, really nice. We have a property of natural laws that says, hey, if you ever are dividing inside of a natural log, you could just subtract two smaller natural logs. Division inside becomes subtraction of two logs. Multiplication inside becomes addition of two logs. Now, adding or subtracting inside does not break apart, so I can't break this up. All right, but we did even have another rule that says, hey, an exponent inside can move to the front. All right, so now we could try to take the derivative of this thing, and this is actually going to be a lot easier. The derivative of 2 times the natural log of x would be 2 times 1 over x, minus the derivative of this thing would be 1 over 4x minus 1, times the derivative of the inside would just be 4. All right, so this would be 4 over that thing. I guess this will be 2 over this thing. All right, so these two answers should be the same thing, but they don't quite look it. All right, if you're with me, they don't quite look to be the same, but mathematically they are. The idea is that this is two different fractions. One big fraction, two smaller fractions. We have learned in the past how to go from two smaller fractions into one big one. If we wanted to check this, we'd have to get the same denominator. So the first fraction we'd have to multiply by 4x minus 1. The second fraction I'd have to multiply by an x. So what? 2 times 4, 2 times 1. All right, the 8 and the 4 would reduce. And this 2 times that and that. 2 times 2x is 4x. 2 times -1 is -2. All right, so these two things are the same. right? It's just they look a little bit different. One of these two answers was very, very easy to get. One of them took a whole lot of algebra, a whole lot of work. All right, so usually if we can apply the rules of natural laws first, it will usually simplify up how we do our answers. All right, and that's really nice. We have to remember those two properties, though. Three properties of laws. All right, those three properties again. Exponents inside move to the front to be multiplied. A log being divided inside becomes two logs being subtracted, or multiplication inside of a log becomes two logs being added. Now, it will not work if there's addition or subtraction inside of your log. So this one has this 4x minus 1 inside, so I can't split this one up. Right? It only works if everything's being multiplied, divided, or exponents. All right, so let's see if we can apply that same idea to this. Like, I do not want to do this derivative, all right, in the normal chain rule way, all right? Because this thing, I've got the natural log of this stuff to the 5th power. Yikes. All right, so I've got to do the derivative of a natural log. All right, I've then got to apply the chain rule on this. Then inside of that's a product. Oh, Lord, that's going to be tough. All right, but what I can do is apply those rules of logarithms first. All right, this exponent that's inside can move to the front. I see multiplication, so I can split this into two smaller logs being multiplied. Notice I applied the 5 to both of them. The first one, I could even split up into two things being multiplied. The second one, I can't really do anything with. There's a sign inside of there, so I can't really split that. All right, so then I could even take this exponent and move it to the front. All right, so my normal function can go from this giant thing to these three smaller pieces being added. All right, now why that is nice is that if I want to take the derivative of this, I can do it really quick, really easy. This thing's just a constant. There's no variables here, so that will be 0. The derivative of 10 times the natural log of x is just 10 over x. The derivative of the natural log of x is 1 over x, so 10 over x. Plus 5 times the natural log of sine, taking the derivative, will be 5 over sine of x on the bottom times the derivative of sine of x, cosine of x. All right, so don't need the 0 in the front. This would be my answer. All right, that derivative is a whole lot easier than trying to do the derivative of a natural log, move all this to the bottom, and then do the power rule, and then do the chain rule. The chain rule has the product. Oh my gosh, that would be insane. All right, so it was able to do this very quick, very easy, without having to use all of those rules. Right, we can just use the rules of logs, which are a whole lot easier first. All right, so the next question is, what happens if the base is not e, or if the log is not base e? Okay, in general, if we're not dealing with e, we're dealing with another number, a 2, a 3, a 10. What happens? Well, the derivative of b to the x, so for instance, example 1 here, 3 to the x. To do that derivative, well, you just leave it, 3 to the x, but then you times by the natural log of that base. All right, so it's kind of like a chain rule, but instead of doing the derivative of the base or whatever it is, it's just the natural log of the base. Okay, so the derivative of something other than e to the x, 3 to the x, for instance, is still 3 to the x, but times the natural log of 3. Okay, that's a constant. All right, not a variable, but you do have to kind of chain it on. All right, so the derivative of the log base 4 of x. Well, the derivative of a natural log was 1 over x. So the derivative of, I guess, something other than log base e, we have to times on the bottom the natural log of that base, and our base here is 4. All right, so x times the natural log of 4 on the bottom of a fraction. All right, so that's just kind of how these work. If you're doing the derivative of something other than base e, we kind of have to tack it on a natural log of that base with our derivatives. All right, so to do this one, I see what's a quotient. So to do f prime, the derivative of the top, 3x times the natural log of 3 times the bottom left alone, minus the derivative of the bottom times the top left alone over the bottom squared. Now, I do see that all these have an x, so we could reduce this just a little bit. 3 to the x ln of 3 times x minus 2 times 3 to the x over x cubed. We could do that. Now, be careful as you're doing things with logs and bases. Like I see this 2 and I see this 3, and I really want to multiply them together and make a 6. You cannot do that. This 3 has that exponent. That 2 does not have that same exponent, so you cannot multiply that 2 and that 3. All right, they do have to stay separated by that times sign. All right, so just be careful as you're doing some of these things. Remember your laws of exponents. All right, let's do this log base 2 of 3x plus 4. Now, these are being added in the middle, so I can't split up this log into two smaller ones. I just have to do the derivative as I know it. So the derivative of a log base 2 is 1 over the inside times the natural log of 2. That's not a base e, that's not a natural log, so I have to times the natural log of that base. But since there's stuff inside of here that's not just an x, I do have to do the chain rule, multiply by the derivative of the inside, which is 3. So we have this answer here, 3 over 3x plus 4 times the natural log of 2. All right, so one really nice thing about logarithms is that we can then do this thing called logarithmic differentiation. All right, to do this type of a derivative, all right, we have this thing to this power. All right, and this power is weird. The power here is a function, not just an exponent. So when the power is a function, all right, and not just a 2, a 5, we can't do the power rule, okay? So like the power rule would say move this to the front and then subtract 1 from this. But this is not just a number. You can't do the power rule when the power is sine of x. That's a function, okay? So we can't do that. But what we can do is this thing called logarithmic differentiation. The idea is we say this is y equals, all right, and we apply logarithms, okay? I take the logarithm of both sides. Now, we're going to use the natural log. As long as we do it to both sides, you can use whatever log you like. Natural log's the best choice. So the natural log of y equals the natural log of this fun thing. Now, the reason we do this is that what was the rule about natural logs and exponents inside of them? Well, they move to the front. All right, and so what we liked about doing this is that by taking the natural log, that weird power, all right, gets moved to the front. All right, so now we can take the derivative. The derivative of the natural log is 1 over y, but since it's more than just a y, we have that dy dx, the implicit differentiation along with logarithmic differentiation. All right, it's then equal to the derivative of sine is a product, so the derivative of sine, cosine, times the second thing left alone, plus first thing times the derivative of the second. Derivative of natural log is 1 over this stuff inside times the bottom derivative, the inside derivative, which is just a power rule. 2 times 4 is 8x cubed. All right, from here, we need to go ahead and get that derivative by itself. So I need to multiply both sides by y. Right, and so last but not least, we do in fact know what our y is equal to. It's equal to this wonderful equation. So my y becomes 2x to the 4th plus 1 sine of x to the power of sine of x times this giant thing. All right, so an absolute terrible looking answer. But if you kind of understand how terrible of a function this is, it should make sense. All right, this function is an exponential with a weird base, okay, that does not have just an x as an exponent, but a function as an exponent. If we were just going to try our best to take the derivative of that, I don't even know where you would start, to be honest. We can't do a power rule to then do the chain rule. You can't do those things, okay? Since that power is not just an x, it's not considered just an exponential. Since that power is not a number, you can't do the power rule. So that logarithmic differentiation is what's going to allow this. All right, same idea with this one. All right, so for this one, x to the x, very interesting idea. So take whatever number you have and raise it to that same power. So like 2 to the second, 3 to the third, 4 to the fifth. No, I didn't say that right. 2 to the second, 3 to the third, 4 to the fourth, 5 to the 5, but also decimals like 1.1 to the 1.1. All of those things, okay? And we want to find the derivative of this thing, okay? Well, do we apply the power rule? Well, no, we can't apply the power rule because the exponent is not just a base number, okay? It's a changing thing, it's a variable. So we can't apply the power rule. Can we apply just the exponential rule, right? When the base is not an e, when it's a number, we use this rule. Well, the problem is the base here is changing, okay? So we can't do the power rule because the power is changing. We can't do the exponential rule because the base is changing. So we have to apply that logarithmic differentiation again. So we say y equals x to the x. We take the natural log of both sides. Now by taking the natural log of x to the x, I can say this is x times the natural log of x. Okay, the exponents move to the front. We can now take the derivative. So the derivative of the natural log of y is 1 over y times dy dx. Because that is not an x, that's a y. So we have to tack on that derivative. This is a product rule. So derivative of the first thing times the second thing left alone, plus the first thing times the derivative of the second. Great. Get our dy dx by itself. Now this x divided by x will just make 1, so that's fun. And our y is x to the x times the natural log of x plus 1. All right, so we can do this logarithmic differentiation, hopefully. Again, we do this idea, take the log of both sides, when the power is something really weird, all right? And the base is also not just a normal constant number. So if you have a weird power or a normal power, but a weird base, okay, or weird base and weird power, all right, when there are variables in both of those two places, not just one of those two places, but both of those two places, we can apply this logarithmic differentiation.